What could your favorite pair of headphones, a fighter jet, and a single living cell possibly have in common? It sounds like a setup for a bad joke, right? But they all actually share a secret language. It's a way of describing how they react to the world, a language built on rhythm and timing. And today, we're going to learn how to speak it.
Okay, let's kick things off with something we all get, something we all have an opinion on: sound. I mean, how do you even describe how a pair of headphones sounds? You might say the bass is punchy or the highs are clear, but it's also so personal, so subjective. And that really is the heart of the problem, isn't it? Like this Redditor says, my idea of warm and rich could be what you call muddy and dull. We need some common ground, right? An objective way to actually talk about what we're hearing.
So, what if we could just cut through all the opinions? What if we could take that totally subjective experience of listening and just turn it into a picture, a graph that shows us the raw, unfiltered data of the sound itself?
Well, guess what? We can. This is it. This squiggly line is the sonic fingerprint of a pair of headphones. It's called a frequency response curve, and it is literally a visual map of how that device reproduces every single sound, from the deepest bass rumble to the highest, faintest shimmer.
And it's way simpler than it looks, I promise. Just look at the two axes. The one along the bottom, the x-axis, that's just frequency or pitch. It goes from deep, thumping bass on the left all the way to super high-pitched treble on the right, basically the entire range of human hearing. And the axis going up and down, the y-axis, that's just the volume for each of those frequencies. So a big bump on the left side, that means punchy bass. A dip on the right, maybe a less sparkly sound. Simple. Now here's where things get really, really cool. This whole idea of a sonic signature isn't just for audiophiles. It's a fundamental tool that scientists and engineers use to understand and even control pretty much any system you can possibly imagine.
So the official term for this is frequency response. And all it is, really, is the measured reaction of a system when you poke it with a super simple, pure tone, a sine wave. I love this analogy. It's like a personality test for anything. You give the system a simple, predictable little push, and you watch very carefully to see exactly how it pushes back.
And the test is always the same, no matter what you're looking at. First, you send in a clean, simple sine wave at one specific frequency. Then you measure the sine wave that comes out the other side. You're looking for two things. Did the signal get louder or softer? That's its amplitude. And did it get delayed a little bit? That's its phase. Then you just do it again and again and again for all the frequencies you care about.
This is a fantastic way to picture what's happening. Imagine you're pushing this mass on a spring back and forth with a perfectly smooth, steady rhythm. That's your input sine wave. Now, how the mass actually moves, how far it goes, and whether it keeps up with you or kind of lags behind, that's the output. The frequency response tells you exactly how that spring is going to behave, no matter how fast or slow you push it.
All right, so how do we actually visualize all this data we're collecting? Well, engineers have a universal standard for this. It's the go-to tool for understanding frequency response, and it's called a Bode plot. Okay, here it is. And I know, at first glance, it might look a little intense, but stick with me. It's actually just two simple stories being told at the same time, one on top of the other. The top graph is all about loudness, and the bottom one is all about timing. That's it. Let's start with the top half. That's the magnitude plot. Just like with our headphone graph, this shows us how the system changes the strength or amplitude of the signal. If that line goes above 0, the signal is getting a boost. It's being amplified. If it drops below 0, it's being turned down. And then there's the bottom half, the phase plot. This one's all about timing. It shows us the delay, or what's called the phase shift, between what you put in and what you get out. A negative number here just means the output is lagging behind the input, which, is usually what happens. So here's a key secret to reading these plots. The frequency axis along the bottom, it isn't linear like a ruler. It's logarithmic. What that means is that every major step isn't adding a number, it's multiplying by 10. So the space between 1 and 10 is the same as the space between 10 and 100 or 100 and 1,000. Each of these 10x jumps has a name. It's called a decade. And engineers use this logarithmic scale to their advantage. It means the shape of the line, and especially its slope, tells them everything they need to know. For example, a perfectly straight line that drops at a slope of minus 20 decibels per decade tells an engineer that a very specific component is in that system. They can literally read the system's blueprint right from the graph. It's incredibly powerful. Okay, so we can draw these charts for headphones and for springs. Cool, but so what? Why is this considered one of the most important tools in all of modern engineering and, believe it or not, even in biology? Yeah, what is the point? Why go through all this trouble of poking systems with sine waves and drawing these complicated plots? Because, and this is not an exaggeration, it can be the difference between a system that works perfectly and a system that suffers a catastrophic failure. I mean, the applications are they're everywhere. Engineers use this to make sure airplanes fly straight, that industrial robots don't shake themselves to pieces, and that our power grid doesn't collapse. We've already seen it with audio gear, and now biologists are using the exact same tool to decode the incredibly complex networks inside living cells. For an engineer trying to keep a system stable, it all comes down to two magic numbers you can read right off a Bode plot: the gain margin and the phase margin. The best way to think of them is as safety buffers. Phase margin tells you how much extra time delay a system can handle before it goes haywire. Gain margin tells you how much extra amplification it can take. If either of those safety buffers drops to zero, you've got a problem. A drone starts tumbling out of the sky. A robot arm starts shaking violently. And this idea of stability and feedback isn't just for machines. This is where things get truly mind-bending. Biologists realized that a cell's internal machinery, all its genes and proteins, it acts just like an electronic circuit. They can treat things like hormones as inputs, measure the cell's response as the output, and create a Bode plot for a living thing. Now check this out. This is the actual Bode plot for a biological feedback loop. See that enormous spike right there? That's called a resonance peak. It tells you the exact frequency where that cell's network is the most sensitive, where it amplifies a signal the most. And if you push it just a little bit at that frequency, the system can suddenly break into spontaneous, rhythmic oscillations. This is how many biological clocks actually work. So you see, from the sound bouncing around in your ears to the complex feedback loops running inside your own cells, frequency response gives us this powerful, universal language. It lets us describe, predict, and ultimately understand how almost any complex system behaves. So at the end of the day, what's the big takeaway here? It's basically a 3-step playbook for understanding almost anything. First, you probe a system with a simple sine wave. Second, you visualize its response, both the loudness and the timing, on a Bode plot. And third, you just read the story that the system tells you through the unique shapes of those two curves. It's a method for turning mind-boggling complexity into something clear. And that leaves us with a pretty wild thought, doesn't it? This method works because it gets at the fundamental properties of any system with inputs, outputs, and feedback. So what else could we look at this way? What would the Bode plot of the global economy look like, or of a social media network? What hidden resonances, what dangerous instabilities might we find if we just knew how to look?